the organizer, the leadership of the AI Institute for inviting me. I'm very honored to be attending this 5th anniversary. I want to congratulate the Institute of this success so far, and I wish many more success going forward on this anniversary. So today in my talk, I will not present all the work we're doing at IVADO, but I pick one part of the topic that is particularly interesting to me as well, to give you a glimpse of the type of work that we have been doing in my group, and hopefully by the end of the talks in a broader ecosystem at IVADO. And I hope we can identify some synergies within the topics and potentially will lead to more fruitful interaction and collaboration going forward. So the topic of my talk today is more about the engineering side of bringing AI system in production. So it's not a talk about learning challenges, but it's mostly a talk about challenges in bringing learned model in productions. So we're interested in trustworthiness, and as you can see from this picture, to achieve trustworthiness, there is a myriad of challenges underneath that we need to unlock, both on the learning sides, on the data intelligence, on the implementation sides, and most recently, and even more actively, also on the ethics and alignment side. So this is the scope of my personal research agenda and also the agenda of many people I collaborate with. Before I dive further, I just want to give a bit snapshot of some of the fantastic people I have in my group. So these are my students. So some of the work I will be presenting in the upcoming slides have been done in collaboration with them. They are all part of IVADO. It gives you a sense of the youth that we have at the institute and in the ecosystem supporting the research that we're doing forward. Okay. We're all aware that we are living the AI revolution. That's why we're so excited about building this pillar to push this research going forward. One of my favorite use cases in this specific setting is the autonomous driving. One of the reasons we are getting close to automate such a complex task as navigation, it's thanks to the multiple success we had on the AI field, in particular in the computer vision domain. With advance in computer vision, we have been able to process information in the point that we can give a sense of sight to autonomous driving assist systems. But given the safety critical nature of this task, navigating such complex urban environment, it's very critical that what we implement in those systems be fully reliable. And implementing AI systems in such complex system is actually in general very challenging. If you take the cases of typical autonomous driving system, in this case is Apollo, usually you have at least more than 30 and 40 AI components in the systems, sensing the information, processing the information sensed from the environment, and integrate it and exchanging information across the different components, which make it even more challenging to handle issues and uncertainty in those models. Why is this challenging to ensure safe deployment of AI systems? Well, we all know one of the main root causes is the nature of the statistical learning process. Deep learning is, for example, notoriously known to be quite brittle. I'm sure everyone in the room have seen this very popular example in the cases where you can easily trick a perception system powered by deep learning in misleading a stop sign with a speed limit, which is a significant safety issue. So how can we prevent such issue when we build system and deploy on the field? Well, one issue could be to have more robust learning, which is one of the agenda that we have at the Institute to actually improve learning approach. But also, we can build more safety guarantees around the behavior of the system. We need a good understanding of the systems, and we need to be able to control the system in production. Another main issue that we struggle with is the generalization. I'm not sure how I can play this, but this is a fun clip that I usually like to have in talks. in the sense it shows we know that most of these learning techniques are very good in distributions. So this is a real case of an autonomous systems already fully deployed. But as you can see here, the system is faced with corner cases that he wasn't aware of. He haven't been trained with some data. So out of distribution is an issue that is still very challenging when we try to deploy those systems. Another common issue with statistical learning, it's biases. We learn from data, which means the data, it's like encoding part of the biases, which make it very challenging to actually build systems that are bias-free. So we need specific techniques to actually handle this type of issue. One other characteristic of statistical learning, which becomes prominent when we put them in production, is the fact that they actually can leak information. Which means that when we learn from data and we deploy in real systems, ensuring the security of those systems becomes more challenging and more significant than what we accustomed at doing. And this issue is actually much amplified when we deal with large language models. So this is the result of a study from Stanford, which appeared later last year, where they actually investigate the characteristics of very prominent language models at the time. And as you can see, although they are trained with the aim of generalizations, in general, large capacity learning models tend to memorize information, which can actually be extracted, and then lead to significant security issues. We already saw in the previous talks, and we were aware that they hallucinate, and this hallucination can actually lead to significant problems. So these are some of the challenges that researchers, including my team, have been working hard to tackle on the field. Another big problem with learning models is their black box nature. In general, the high-performing models are very hard to explain. Of course, there have been many attempts of building explanation techniques to try to make sense of the decision logic of models. But the reality is they are still not fully trustworthy, and in general, they actually disagree. So when we try to explain model post hoc after the model being trained, most of the techniques rely on approximating the behavior of the model. And multiple studies, including some from our group, have shown that this leads usually to disagreement. And the disagreement problem makes it very difficult to apply them in practice. The fact that it's difficult to implement that in practice makes it challenging to audit systems that contain this type of component. In a recent studies that we published last year at ICLR, we investigate one of these most popular possessive explanation technique, which is SHARP. And what we found is that you can actually manipulate the behavior of this model. Just by selectively sampling the manifold, you can reconstruct the distribution and obfuscate the contributions of different features. So explainability is still a significant challenge when we deal with model. And this challenge is actually one we have to face because given the increasing effort on regulating systems, most of the regulation that are being produced require full transparency, or at least to make sense of the behavior of the system once they are deployed in production. And a recent study by Stanford High, we actually investigate the compliance of very popular and prominent language model with respect to the EU Act, found most of them not to be compliant. So on the learning side, we still have significant challenge to ensure the trustworthiness of the model once we try to put them in production. So to engineer safe and trustworthy AI systems, we need to move past the accuracy of the system. We need systems that are explainable, fair to some extent, privacy preserving, more causality it's usually aimed for, and then we need to ensure their robustness. So how do we tackle this problem? And even more significant, when we deploy AI component into systems, we need not to limit our implementation to the component implementing the algorithm, but to the whole system view, because the AI model is usually just a small part of a full stack of the system. So in my research, we mostly look at the system approach of this. And this is our view that to improve the robustness and the reliability of systems in production, we need to account for the interactions between the components as well. So this year at AI Start, we published a work where we try to tackle the disagreement problem. So how can we reconcile disagreement between different post-hoc explanation techniques? One observation that we made is that for additive models, the disagreement is actually very limited. So with practical approach, such as decomposing the input space of a model and provide local regional explanation instead of global explanation, we were able actually to minimize these interactions, minimize disagreements, and improve the trustworthiness between different post-hoc explanation techniques. So this is just to give a glimpse of the type of work that we do on the XAI domain, more on the theory side of the work. And as you can see on some of these examples, as we decompose the domain, we have better alignment between techniques. So it's possible to approximate the behavior of AI models, but it requires clever implementations. And so more research is needed to actually tackle this problem, to ensure more trustworthiness. One area where we are also very particularly active, it's on the implementations of the model. How can we ensure that the model that we deploy are actually behaving as expected? Typically, when we train a machine learning model, we go through different typical steps, which generates multiple artifacts in which it's actually, some of them could actually be erroneous. So some of the work that we do is actually to try to analyze the artifact generated during the training process of model and develop techniques that can enable quality control throughout the generation process. So as we make our design choices, we decide how to optimize the learning process, we want to be able to detect issues that could occur. And how do we do this? We want to develop techniques that allow us to anticipate on the failures of the model early on during the training process. So comparing to traditional systems, when you build a machine learning model, the range of issues that you have to face is way broader. So we have training issues, which increase security risk. We have implementation issues. It's good. And also we have data issues. Which require specialized techniques to be able to detect this issue on the models before being deployed in productions. On top of that, finding errors in statistical learn program is actually usually very tricky. What are the reasons why it's tricky? It's because of the nature of these errors. So in general, these errors are quite brittle, and the learning process is very sensitive. So finding this issue in a trial and error model is not efficient. So in our team, we actually develop techniques that allow to process automatically the training process and identifies issues. So we have been building tools that are available, or can be downloaded when you access the Institute website. We build tools both via static analysis of the program, but also a dynamic analysis of the program. So one of the key pillars that is used to develop those tools is program analysis. So we probe the programs and build a representation that allow to detect these issues early on in the process. We also develop dynamic analysis tools by leveraging properties-based techniques to extract information during the training process and detect issues. So we're able to detect on training issues like poor weight initializations when there is issue of convergence when they are exploding gradient, we could detect this issue early on before the model being deployed. This significantly saves cost when you train large model at scale. So this is for the code, and once we ensure the safety of the training pipeline, we have the model. So before the model being deployed in production, it's important to assess the robustness of the model. So we have been working on developing adversarial robustness techniques. Multiple research in our group have proposed these techniques. But here, this research has been done in general in collaboration with our industry partners. So I want to show you a brief example of some of the work on how we have been successful at deploying theoretical work conducted in practical applications in the industry. So this is the work in collaboration with one of our industry partners, which is a robotic company. And the goal in this work is to ensure the reliability of this robotic arm in a cost-efficient way. So how do we achieve this? The model, it's a vision perception model relying on neural networks. We want to bridge the gap between the train phase of the model and the real deployment of the model. So in this work, we leverage in simulation-based. One of the reasons we rely on the simulation instead of adversarial robustness, it's because it allows us to interact with the deployment environment of the robotic arm. So we developed these techniques which allow to synthesize the environment in which the robotic arm is to be deployed, search for failures in the behavior of the robotic arms, and automatically repair the robotic arms in simulations before being deployed in the real hardware. And after deployment in the real hardware, we sample the behavior of the robotic arm and it further improve through few steps of fine-tuning the behavior of the model. So these are engineering approach that allow to improve the safety of this component. And this process, one interesting thing is this project is that through this process, we could actually discover system-level errors, which stem from the interaction between the learned component and the other component in the robotic arm. So to give you a bird view of how the steps proceed. Okay, I'm struggling a bit with this clicker. So we acquire scenes, and we had these two use cases. So here we were interested in assessing the robustness of this arm. A section base and a grouping base. We wanted to look for errors in the behavior of the model during the training phase and repair the model on the fly before being deployed in production. So we randomize the environment of the models and then use it to train the neural networks. And the important phase is using the representation of that environment, we could actually search with evolutionary algorithm for errors during the behavior of the models. And after we found these errors, we use them to actually correct the behavior of the model. So using evolutionary search, because we know that there's no free lunch, we experiment with different evolutionary techniques. And as you can see, these allow to uncover a significant amount of error before the models being deployed. After these steps, the model is fine-tuned, which improves its behavior. And deploy in the real hardware. So combining in simulation with real-world data significantly improve the behavior of the models. I have too many animations in this part, I feel. Yeah. Okay. And this process allows us to detect system-level errors. For example, if you look at these two cases, we actually uncover errors in the systems that couldn't be correct because of limitations on the hard robotic arms of the system, not only the software. So this allowed to characterize the operation domains and improve the safety of this robotic arm, which is now safely deployed in production. So in this example, I just wanted to give a glimpse of how academic and industry collaboration and research actually lead to significant safety improvement on products in production. So the approach revealed up to 50% more errors and led to system-level discovery. And with only limited fine-tuning of the DNN, we could actually significantly improve the performance of the model. We also had another use cases. In this case, this project was conducted with Bombardier, which is the Canadian aerospace company. We were interested in supporting the aircraft design process, which is an incremental design process, very costly in general. And in this case, they were interested in building a statistic learning-based model to be able to predict the impact of design decision on the aircraft on the behavior of the aircraft. So we're interested in different stages of the flight. And since this is a safety critical system, so one important property was the robustness of the models that were to be deployed. So we needed to be able to have a precise understanding of the operation domains of the models and be able to characterize this model. And in this project, which I will go in more detail, we leverage statistical learning and exploit the smoothness properties of the systems to be able to build a tool to detect out of distribution input of the model and characterize the operation design domain of the aircraft in real time. And this tool have been successfully deployed in the company and is actually functioning. Researchers in our groups have also been supporting the development of reinforcement learning techniques, proposing frameworks to allow to probe the behavior of reinforcement learning agents through the development process to improve their reliability and their safety. For example, this tool is able to detect different type of errors. So if you have been accustomed in training reinforcement learning agent, you know it's notoriously difficult to actually identify issue during the training process as the agent is interacting with the environment and optimizing its reward. Automatically finding this issue in production is actually costly. So this tool has been proposed to actually monitor the training process, extract information, and provide signals about the behavior of the system at the system it's being deployed. And it has been successfully adopted in our ecosystems, and the result shows that it significantly improves the reliability of the systems with very limited overhead when implemented in practice. So leveraging these different tools enable to improve the reliability and safety of the component before these components are deployed in practice. So more recently, with the increasing development of large language model, an area in which some of our group have been becoming active, it's the area of leveraging AI to support the development of software systems. We are seeing now more and more AI-assisted tools being used to produce systems to produce code that are built in the systems. If you look at the statistic produced, the adoption of these tools such as Copilot, I'm sure many people have been accustomed to, are actually significantly high, with many teams reporting increased productivity. So how can we ensure the reliability of such tools that are playing a significant critical role in the development of high-performance systems? So some of the work that we have been doing have been to improve learning techniques that aim at supporting the development process. of software systems, not only on the code generation phases, but all through the development cycle of software systems, including the review phase, the test case generation phase. And one of the early work that we have done on this topic, once GitHub Copilot was released, was to understand the nature of issues that this type of tools brings to the development process. So we investigated the characteristics of coding artifacts generated by these assistants. And one interesting thing that we observed, despite their limited capability in handling complex tasks, is that the signals that is generated by these coding artifacts is actually significantly different from the signals generated by humans developers. We conducted studies to characterize these differences, the type of issues that are commonly occurring when we learn to code, and we also analyze the security vulnerabilities of the coding artifacts that are produced through learning-based algorithms. And as you can see on this result, there is a significant amount of different type of vulnerability frequently occur by this type of system. So the big question we have was, how can we further improve the reliability of this system by improving the learning process? So in subsequent work, we leverage in-context learning to refine the behavior of language model for coding tasks. And results shows that you can actually, to some extent, mitigate some of the trustworthiness issues that emerge from those models. We could improve the reliability of the coding artifacts that are produced, and we could also improve the efficiency of model built on language model for coding in this. So you can see on this result how the performance of the model have been improved and increased as the adoption of these techniques have been deployed in practices. We also conducted research on the operation side. So once we have built the models, ensure the safety of the training process, improve the robustness of the models, and now the models are deployed in systems in practice. A frequent issue that we face when we deploy models in practice is the drift of the environment. So as the system is being deployed in non-stationary settings, the behavior of the model drifts over time. So how can we, through engineering mechanisms, preserve the behavior of the model deployed in production? We have been conducting some work to improve the perplexity of reinforcement learning agents, allowing the agents to adapt to changes in the environments by selectively improve the behavior of the agents. So there is an increasing interest on this type of techniques. Some result from my research group and some result from other researchers from the IVADO ecosystems, leveraging continuous learning approach to improve the reliability of such agent. So this is just a glimpse of the work that we've been doing in my group, but at the institute level, we federate the efforts of 16 research centers to look into these issues among other issues. The key of our agenda is to improve the robustness of learning algorithm, to improve the responsible adoption of these techniques, and interestingly, improving their reasoning capability. So there have been some work in our institute from other research groups working at developing more system 2 type of reasoning in learning systems. And the goal of the programs is to leverage this advance on the learning and deployment phases to fuel innovation in other domains. So we are very active in the drug discovery space, the material design space, the logistics space, where we leverage advances on the learning techniques to support fundamental research on those spaces. The research agenda in the institute have been organized in 10 research clusters. So we have a research cluster on neuro AI. In that group, researchers are exploring the intersection. The goal in that group is to deepen the understanding of the behavior of the brain to improve the design of learning algorithms. So this is a research consortium that have been very active already and have ongoing activities. We have a research cluster on fundamental machine learning research, where we work on more statistical learning challenges and pushing forwards the boundary of the learning process. We have a cluster on natural language processes, where the current focus in that group has been on transformers, language model-based agents, multi-agents, and the safety of the agents. And next year, actually, we're running a thematic year on transformers in Montreal. We're collaborating with the Simon Institute in the first part of the year at Simons, running 3 workshops on language models and transformers, on their theoretical properties. And then in the second phase of the years, we'll be running the rest of the semester in Montreal on multi-agent. So everyone is welcome to join if you have interest in language models and transformers. We also have a cluster on the implementation science of AI systems and governance, which is one of the clusters that I'm co-leading with some of my research peers. In that cluster, our focus is to develop techniques similar to those that I presented in my talk to support the safe and reliable deployment of AI-based components in practices. We have a cluster on material and molecules. We also have a cluster on environments, where researchers leverage AI for environment issues to get a better understanding of biodiversity, to get a better understanding of climate change issues. We have a healthcare systems clusters, where AI is leveraged to improve the quality of care. There is a lot of research in that group on personalized medicines. There is research in that group on improving the supply chains of medical care systems. We also have a cluster on logistics and supply chains, where researchers are dealing with more optimizing the logistic, the supply chain systems, is similar to what have been presented in the talks just right up before me. And last but not least, we have a cluster on AI safety and alignment. So this cluster is actually co-led by Joshua. The goal in this cluster is actually to improve safety guarantee on the learning process. So one of the big questions that we're looking in that cluster is how we can train agents that are self-aware of their limitation, how we can ensure that as a training objective, we include safety, in addition to the downstream objective that we're interested when training the models. So that cluster is very active on the safety and governance issues, both on the theoretical part and also on the social aspect of the issue. So I hope I gave you a glimpse, if just a small glimpse, of some of the works that we have been doing in my team and at the IVADO ecosystems in more abroad. And I will be happy if you have any questions for me.